So a few definitions to start out with in this section. We're going to talk about probability distributions. We're going to look at the mean and standard deviation of these distributions. But for starters, let's understand what a random variable is. So a random variable is a variable typically measured by x that has a single numerical value determined by chance. So that's one important characteristic of random variables. Now, a probability distribution is going to list for you the chances of that particular value of x occurring. So it's either a description in terms of a table like this, or maybe it's a formula that allows you to calculate the probability of the occurrence of each value of a random variable. So could be a graph, could be a table, could be a formula. Now there's a couple different types of random variables that you can deal with. You could have a continuous random variable, or you could have a discrete random variable. Now one thing that's true, it has to be a random variable. It has to be a numerical value that's determined by chance. So for instance, this one down here, the eye color of people on a commercial airline flight. Why is that not a random variable? That's not a random variable. Yeah, because it's not a number. It's just your eye color, or excuse me, in this case, yeah, your eye color. So it's not a random variable because it's not a numerical value. Now, if it is a numerical value, then we're going to distinguish between a discrete random variable and a continuous random variable. Now, for a continuous random variable, that can be anything within a certain number range. So it can take on any value in a range. Maybe, for example, e.g. 0 to 10, you could have any value in there as your continuous random variable. A discrete random variable, typically these are things that you can count, so that, you know, it can't be just anything in an interval. This is things that you can count. You can't count the number of points in this interval. There's an infinite number of points. But with a discrete random variable, you can. So here, this can take on countably many intervals. It can take on countably many values. But it's not continuous. It can't take on just any particular value. There's gaps in between the values that it can take on. So for instance, when we look at the number of points scored during a basketball game, can you score 8.6 points or square root of 2 points? No. There's a lot of gaps in there. But you can score 10 or 12 or lots of other possibilities, you know, hopefully closer to 100, but it can, you know, it is a discrete random variable. So I'm just going to kind of color code these. This one's a discrete random variable. How about the time that it takes to fly from Detroit to Chicago? The time of your flight. Is that a discrete random variable or a continuous random variable? Could it be any time in some interval? Yeah. So if it can be anything within some interval, then it's a continuous random variable. We already did example C here, so let's move on down to example D. Time it takes for a light bulb to burn out. Well, this is another time question, so that one's kind of the same as B. It's going to be something in an interval. The number of statistics students now reading a book. Can that be a continuous random variable? No, you can't have 3.14 statistics students reading a book. It's 3 or 4 or 5 or whatever, but it's a discrete quantity. Same thing with the number of free throw attempts. You can't have those numbers in between. So it's a discrete random variable. Now when you're describing your random variable and you want to determine if something is a probability distribution, there's going to be two requirements. That first requirement is that each of your probabilities has to fall within some interval. Where do our probabilities lie? Where are you going to find your probabilities? What's the most or least a probability can be? 0 to 1. So that's right here. So in order to be a probability distribution, each of these probabilities has to be between 0 and 1. So that's our first requirement. The second requirement is that the sum of all the probabilities, if I add up this list, what do you think I should get when I sum up that list? Should be a 1. The total of the probabilities sums up to 1. And that makes sense, because if you're looking at something that happens by chance, and if you add up all the different possibilities, it should sum up to 1 because something will happen amongst all your different possibilities. So that's what that second part is saying. Now, when we do these things, occasionally what you'll see is something summing up to 0.999 or 1.001. Typically speaking, that's a rounding error. All right? If I asked you if something was a distribution and I wanted you to conclude no because it didn't sum up to 1, it would make it pretty far away from 1 so that it's clear it wasn't a rounding error. It'd be like a 0.86 or a 1.07. So that's it's like, okay, that's far enough away that it's not just an accidental rounding error. Let's move down to kind of a fun example that I want to start with, which is example C here. Rolling a pair of dice. So what I have here listed for you is your sample space for rolling a pair of dice. How many things can happen? How many different points are there in my sample space? 36. I hope you didn't count, right? It's just 6 times 6, so that's 36. That's how many points in our sample space. How many ways are there that I can roll a 4? How many ways are there that I can get a number of 4 between the two dice? A total of 4 on those two dice. 3. 1, 2, 3. And if you look here, the probability of a 4 is 3 out of 36. Okay, that makes sense. Here it is as a decimal. So that's nice. Now I left them as fractions here because here they total up pretty nicely. What do you think that total would be? (36 out of 36). Or better yet, 1. Now like I said, you might see a little bit of rounding error occasionally on these problems, but let's take a look at our tab here for C, and I've got the probability listed all the way down here. I mean, suppose you could do, 36 out of 36 here. Just type it in for yourself. As long as you don't hit the equals key, it's not going to chirp at you. All right, but we got a 1 here. That's what we expected. Well, here's where we're headed with this section. We want to try and figure out, well, what's the probability that, or what would you expect if you were rolling a pair of dice again and again and again and again? What would you expect? So let's take a look back at this thing real quick. What do you think the most likely outcome of a pair of dice is going to be? What do you think you're going to see most often when you roll a pair of dice? 7. Yeah. That can occur 6 times out of the 36 ways, or a 1 in 6 chance of seeing a 7. But oftentimes what we want to do is we want to figure out, well, what's going to happen on average when you play this game? If you were to roll, a pair of dice thousands and thousands of times, what's your average roll going to be? And that's going to be something called your expected value. So let's figure out what the expected value is for a pair of dice. Now, the expected value also has a couple other different ways we can refer to it. We can refer to it as the mean, or we can refer to it by the symbol for the population mean. Does anyone remember what the symbol for a population mean is? Mu. There's your mu. Now, to figure out the expected value for a probability distribution, you've got to take and calculate the product of x, which is here in this row, times p of x, which is up here, x times p of x, actually I guess I should do it here, x times p of x, and then we got to sum that up. So it's going to be the sum of x times p of x, and that's going to be your population mean. So let's take a look at what that's going to be for our particular sheet here. And so here's my x times p of x. And if you take a look here, here's kind of a cool thing you can do. If you click on the formula, it'll highlight the cells that it's using. So I'm using this cell and this cell to get this product. So that's kind of a nice little debugging thing if you ever need to. So I'll just click that one. Now that one's already been done for us. If you sum that all up, you should get the number 7. And so 7 is the average roll when you roll a pair of dice. Now this number doesn't have to be something you can actually get. It does work out in this case that you get a 7. If I was doing this experiment with 1 die, what do you think the average roll with 1 die would be? If it with 2 it's 7, what's with 1 die? What do you think would you get? 3.5. 3.5, yeah. And the weird thing is that you can't roll a 3.5, right? You can roll a 3 or a 4, but you can't roll a 3.5. But a 3.5 would be your average roll. That's what's going to happen if you do this experiment time and time again. Now, after we covered the mean in this course, we also covered something else. You remember what we covered in the very next section? It was section 3.2. We found what was typical about our population, and then we found out how much spread there was. What was it that measured the spread of our data? Standard deviation. The standard deviation, I don't have that stuff here, but I do have it in our Google Sheets. To calculate the standard deviation, you need to use this formula. It's here in red. Now, if you want to see what that looks like down here for our calculations, click the cell F4, the first one there, and then you can click up in the formula and you'll see which ones it's highlighting. You're going to take the value of p of x, which is in column D, times x minus mu. Mu for us was the number 7, and I just typed in that number 7. It's important that you not refer to it in any other way. Just type it in, and then I square it. When you copy that formula all the way down to the bottom of your sheet here, you get all these numbers, and you got to do 2 things. First one is you got to sum it up. But when you sum it up, you get the variance, which I denoted as s squared. Okay, that's great. But if I have the variance and I wanted to get the standard deviation, what one other operation I got to do to go from the variance to the standard deviation? Square root. Well done. Well done. Yeah, you take the square root of that. If you take a look at the cell F17, it's just the square root of F16. And that's going to be our standard deviation. Now, back when we covered standard deviation, we said that standard deviation helped us measure how unusual something was. How far away do we have to go from the mean before we started getting some unusual observations? 2 standard deviations. So if you take a look here, if I go 7 minus 2 times the standard deviation, I get to 2.17. And 7 plus 2 times the standard deviation, I get to 11.83. Now this might be a little bit confusing for you when you're trying to look at that and go, wait a minute, you can't get a roll of 2.17 or 11.83 on a pair of dice. And I would say, yeah, you're right. But it still helps us determine the unusual rolls. Let's take a look here. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, oh, perfect, 12. Now, my dividing line was this, 2.13, and what was it, 11.8? 2.13, and 11.83. 11.83. So these are your typical values, or not significant. What does that leave, though? It leaves 2, and 2 is significantly low. And then one more, right? It leaves, let's do it there. It leaves a 12, which is significantly high. So again, the standard deviation is helping us decide what's unusual, significantly high. If you're more than 2 standard deviations away from the mean, that's unusual. You've got a 1 in 36 chance of getting a 2. You've got a 1 in 36 chance of getting a 12. So those are pretty unusual observations. The rest of these, yeah, they're not that significant. Comments or thoughts on example C here? We'll finish up some of this next time. All good here? C.